Hello friends, welcome to another lecture of classical mechanics. Here we're going to find the expression for Hamiltonian of a particle moving under central force, and we're going to find the Hamilton's equation of motion of this particle. Right. So before we start, please subscribe to the channel, hit the thumbs up button. Also share with your friends, inspire me to create new contents for you. And if you want to follow me, this is my Insta ID, ozalekajit123. ozalekajit123. You can follow me on Insta. This is my Insta ID. Okay. So now let's start. What do you mean by particle under central force? Suppose we have a particle. This is a particle, and moving along a curved path. Suppose, and under a force, the force is acting on it, which is towards the acting along towards the fixed point, suppose O. It may be attractive or it may be repulsive as well. Then this force, which is acting, which is directed towards a fixed point, is known as central force. You can take the example of motion of the planets around the sun. This is the orbit, suppose, and here is the planet. Any planet, it may be Earth or something else. So let me take this as a planet, and here is the sun, right? And this is the distance from sun to the planet P. So it's gonna have an aerial velocity, right? Also it's gonna have a linear velocity as well. So this kind of motion are nothing but motion under central force, right? So now you see, suppose if we consider a unit vector along this line OP, in outward direction, we suppose, let us take r cap. Okay, then the central force F, that gonna be given by, that is function of r, Fr, okay, dot r cap, right? So if it is repulsive, that means then its magnitude gonna be greater than 0, okay, which is positive, that means which is along the r cap. And if it is negative, less than 0, then it's gonna be attractive, right? So you can say that. And this central force is also minus partial derivative of r partial derivative of the potential with respect to r, where v is the potential energy of the particle, right? So now let me write all these things what I have explained to you now. So just wait. So these are the things that I have considered. So let me take a curved path. So this is a curved path, and this is the particle P, and here is the fixed point O, and this is nothing but R, right? So we can consider that way, right? So as I have already mentioned, that this central force is given by this expression, and if it is less than 0, then this is attractive. If this is greater than 0, then it is repulsive. And this is also negative, partial derivative of the potential, negative of partial derivative of the potential, right? So we can consider that way. Now you see, let me take a new slide. Here we're going to find the kinetic energy and the potential energy to find the Hamiltonian, right? So let me take a new slide. Just pause the video and take the screenshot, or you can note it if you want to note, right? Just let me go to a new slide. Here you see. So what we're going to do here, let me draw the diagram here again. This is the diagram that I have drawn in the previous slide. So what we're going to do now, here you see. First you must know few things that for the time being, just remember this, that its velocity is given by, its velocity v, that is given by dr by dt, and that's going to be equal to r dot r cap plus r dot theta cap. And remember one thing, this r cap is in this direction, and theta cap is in the direction which is perpendicular to r cap, right? So remember that way. So this is the direction of theta k, right? And this is the expression for V. It has two components, and their magnitudes are, magnitude of each component is this is VR, that is given by r dot, and V theta, that is given by r theta dot. So just for the time being, to understand this explanation, just remember that the velocity of this particle has two components, that is Vr, that is given by r dot. So r dot means dr by dt, simply dr by dt, and one is theta dot, that is d theta, d theta by dt. Okay, remember that way. So if you want to know how I have got this Vr, that is r dot, and V theta, that is r theta dot, if you want me to make another lecture on this separately, then just hit the like button. Okay, when this video gonna get 100 likes, then I'm gonna make another video, and because I'm not gonna explain in the same video because it's gonna be very long. For the time being, you just remember that velocity of this particle is given by this expression, right? This is the velocity of this particle. Remember that. Okay, that's enough for this explanation, for this lecture, to understand this lecture. Okay, so if that is the case, now you see, so what going to be the kinetic energy of this particle? First, let me write the velocity of the particle. P, that is V vector, that is what, dr vector by dt, that is given by r dot r cap plus r theta dot theta cap, and it's gonna have two components. One is Vr, so here r cap plus, so V theta theta cap, where Vr is nothing but r dot, and V theta is equal to r theta dot. That's what we have got. So therefore, kinetic energy of this particle, kinetic energy, let me represent it by T. That's going to be given by, kinetic energy is equal to half mv square. Here V, so we have two components, right? So we're going to take the squares of these two, squares of Vr plus square of V theta as well. So then the kinetic energy will be given by half m. So Vr square means here r dot square plus V theta square means r square theta dot square. That's what we're going to have. So this is the kinetic energy. And potential energy, potential energy we have taken Vr, right? So potential energy is Vr. Okay, so now you see we have potential energy and we have kinetic energy, right? So we can find the Lagrangian. First let us find the Lagrangian. Okay, Lagrangian, that is given by t minus v. Okay, if that is the case, then the Lagrangian L that's going to be given by, we know this is t, so let me write this one here. This is t, Lagrangian L, so we have written t here, minus potential energy is Vr. So we have got the Lagrangian. Okay, so now let me copy this and let me go to a new slide. So what is the Lagrangian that we have got? This is the Lagrangian. If this is the Lagrangian, then we're gonna have we're gonna find momentum. We're gonna have two components of momentum, right? Like the velocity, because we have got two components of velocity, Vr and V theta. Like that way, we're gonna get two components of momentum, Pr and P theta. Let's find these two. So what is the relation between the Lagrangian and momentum? So I have find the Lagrangian, because the momentum PR, that gonna be given by del L by del R dot. So that's why we have obtained here the Lagrangian L. So if you differentiate this with respect to R dot, then here you see this part is containing R dot only. So that's why we're gonna have half M twice R dot. So here 2 gonna be cancelled. So we're gonna have M R dot, right? So which implies R dot is equal to PR by M, and P theta, that gonna be given by del L by del theta dot. So if you differentiate it with respect to theta dot, so this part contains theta dot, this one into half M, right? So if you differentiate it, that gonna be equal to, so remaining part will be 0. Those terms which are not containing, which doesn't contain theta dot, that gonna be 0. Its derivative with respect to theta, that's gonna be 0, and the derivative of this part, so half M into this part, that's gonna be half M R square, theta dot square. Its derivative is 2 theta dot. So here 2 gonna be cancelled. So we're gonna get M R square theta dot, and which implies that theta dot is equal to P theta divided by M R square. That's what we have got. So let it be equation number 1. So now let's find the Hamiltonian. So Hamiltonian is given by H is equal to kinetic energy T plus potential energy V, right? So let's find the Hamiltonian. So we have already got that kinetic energy is half. This is the kinetic energy. So let me simply just write here. So kinetic energy plus potential energy VR, right? This is the Hamiltonian. Now if we simplify this, then what we're going to have, half M R dot square plus half M R square theta dot square plus VR. That's what we're going to have. So now you see this is Hamiltonian, right? So now let me copy this. Now let me go to another slide, new slide. Just let me copy this one. Okay, so here is the new slide, and this is the last step that we have obtained. So now you see one more thing, that from equation number 1, let me copy this result, R dot and theta dot from equation number 1. So what we have got here, these are the equations number 1. So here what we're going to do, we're going to replace the R dot square by this value of R dot, and theta dot will be replaced by this result. Then we're going to have PR square by twice M, because here you see, if you put here this value, right, half M R dot square, R dot is PR by M, so R dot square PR by M square. So in this case, what will happen, PR square by M square, this M cancels M, so we're gonna get this result, right? So hope you have understood this. Similarly, we have used this result here, and using that, after simplification, we're gonna have P theta square by 2mr square plus VR. That's what we're gonna have. So this is the required Hamilton. So here we're gonna write from equation number 1 or using 1. Okay. So this is the Hamiltonian. This is the Hamiltonian for a particle moving under central force, right? So hope you have understood this. So now what we're going to do here, you see, by Hamiltonian canonical equation, by Hamilton canonical equation of motion, PR dot, that is equal to minus del H by del R, right? So if you apply that, if you differentiate this Hamiltonian with respect to R, then what are you going to have? So you're going to have this result. So let me tell you. Now you see, this is PR square by twice M. In this part we have no R as variable, so only this term consists R as variable, that is R square. So if you write here, that's going to be R to the power minus 2, right? If you differentiate it, so P theta square by twice M, that part is constant, so we're going to write as it is, P theta square by twice M. So we have to differentiate partially del R, that 1 by R square. We're going to differentiate it, so there should be a negative sign. So if you differentiate it, then what we're going to have, minus P theta square by twice M. So this is nothing but R to the power minus 2, right? R to the power minus 2. So that's why we're going to have here minus 2, R to the power minus 2 minus 1, that's going to be minus 3. That's what we're going to have, right? Then we have potential VR, which is a function of R. So that's why one more thing we should have here, that is plus del V by del R, right? So here we're going to have del V by del R. Just wait. Del V by del R. So now this minus, that's going to be plus, right? And after differentiation, we're going to get P square by twice M R3, sorry, not R, here these two going to be cancelled, right? So what we're going to get, so we're going to get PR dot, that's going to be equal to P theta square by, so let me take a new slide, okay? Let me take a new slide. Let me copy this last step and let me go to a new slide. So here is the new slide. So what we have got, PR dot, that's equal to P theta square by M R cube plus del V by del R. That's what we have got. And also we're going to get P theta dot is equal to minus del H by del theta, right? So now let me go back to the previous slide. If you observe the, if you see the Hamiltonian, right? So here you see there is no such variable, there is no variable theta, okay, to differentiate with respect to theta. So there is no such term that contains theta as variable here, so that we can differentiate with respect to theta. So that's why this is going to be equal to 0, this is going to be equal to 0, right? So that's what we have got. Now what we can do here, you see, now from equation number 1, let me go back to the last slide where here you see equation number 1. Let me copy the equation number 1, right? Let me write here. From this equation number 1, what we can write? We can write R dot is equal to PR by M, right? From equation number 1 we have got this, right? So that's why let me cut it. What we can do here, we can find R double dot. If we differentiate it again, then what we will have? you're gonna have 1 by m, this part is constant. If you differentiate PR, right, that's gonna be PR dot. Okay, PR dot means if you differentiate it with respect to time, then you're gonna get PR dot, right? So now what we can do here, you see, PR dot, we have got this result. Now let us use this result here. Okay, so let me use this, let me write this as equation number 2. Okay, this is equation number 2. If you use this equation number 2, then what you're gonna have, 1 by m, and you're gonna have this result here, 1 by m into this, from equation number 2, or using 2, simply you can write that way. So if this is the case, then what we're going to do here, so we can write m r double dot is equal to p theta square by m r cube plus del v by del r. That's what we have got. Okay, right. So I think I have missed something here. Let me go back to the previous slide. Now here you see, as we have minus sign here, so it's supposed to be minus, right? It should be minus actually. So if that is the case, here we're gonna get minus. So let me replace this by minus sign. Okay. So sorry for this mistake. So that should be minus. Okay. So now you see here this equation m r double dot p theta square by m r cube minus, here you see we have already told that we have already got that f of r, that is equal to negative of del v by del r. So I have already given this one, right? So at the beginning of this video, so that's why we can replace this term by this central force. So let me copy this, right? Let me copy this. So let me write here. So here f of r is the central force. This is the central force, and this is the equation of motion. This is the equation of motion of the particle under central force, right? And one more thing here, this p theta square by mr whole cube. So we know that p theta is nothing but m r square theta dot square. We have already got this one. So let me go back to the first slide. So here you see, here from equation number 1 we have got this one, right? P theta is equal to this one, right? So which implies theta dot is equal to this, right? So let me replace this p theta here by this value. Then what we're gonna have, m r square theta dot whole square by m r cube, and then what we're gonna have, m r to the power 4 theta dot by m r cube. Here it should be m square. So if you divide it by m, then this square cancels. So then we're gonna have m into, let me keep it keep this one as square, and theta dot, so there should be also square. Okay, then let me cancel these two by r square. Okay, then you're gonna have square here, and here you're gonna have r. Okay, because there is r cube. If you cancel it by r square, then you're gonna have r, right? So now you see this r square theta dot square, this is nothing but we know r theta dot is nothing but v theta, that I have already told you. This is nothing but v theta, right? I have already told you. So that's why it can be written as m v theta square. This is m v theta square by r. This is nothing but centrifugal force, right? So hope you have. So this equation also can be written as, if you use this expression instead of this one, okay, then you can write this way: m r double dot by is equal to m v theta square by r plus fr. So we can write this one as well. So thank you for watching. See you in the next video. Hope you have understood. Please do like the video. Also share with your friends. Hit the thumbs up button. Hit the bell icon. Okay, and do subscribe the channel if you are new to my channel. So thank you.